Log on, tune in, find out. Another good idea from Cambridge.
And today we have one seminar talk for our Discrete integrable systems weekly seminar. And Professor Niskolski's talk was postponed to the next week. And so there will be two talks next week, one by Professor Niskolski and the other by Professor Baxter. Okay? So today's speaker is Professor Hjalmar Rosengren from Chalmers University of Technology, Sweden. And the title of his talk is Three-Colored Chessboards and Baxter's eight-vertex-solid-on-solid model.
Yes, thanks. So my plan was to give an old-fashioned talk with a blackboard, but then I realized I will probably run out of time somehow, and then I will switch to the camera to speed it up a little bit. So actually the things I will speak about are things I've been thinking about for quite a long time, and I had a lot of trouble with, but just the last 1 or 2 weeks I had some new ideas that seem, well, that seem like they solve the problem I want to study, essentially. But it means that, well, there will not be a lot of details omitted, and it's not only because, well, it's good to omit some details. It's because I haven't filled all details in myself either. But anyway, the title is something like three-colored chessboards and so is this is it visible to you if I write here? Yeah, I don't have much choice where to write. Okay, so three-colored chessboards and eight-vertex. Solid-on-solid model. And the background or motivation for all this is really the famous alternating sign matrix conjecture, or nowadays theorem. So so that's quite a well-known story, but let me say just a few words about it. First of all, an alternating sign matrix. It's something like something like this. So the rule is you have a square matrix, and the entries are always 0, 1, or -1. And also if you follow any row or any column and just look at the non-zero entries, they will alternate in sign, and they will also add up to 1. So there has to be at least 1 in each row and column. And if there are 2 ones, there has to be a -1 between them somewhere, and so on. Let me just write down this. So for instance, if you look at the case of 3x3 matrices, then any alternating sign matrix is either a permutation matrix or this single example. So this is the only 3x3 alternating sign matrix that has a -1 in it. So that means that for 3x3 matrices, the number of alternating sign matrices is 7. So the alternating sign matrix conjecture is to compute the number of such things. And that's a nice result that was conjectured by Mills. Robbins and Ramsey in 1983, I think. Yes. Well, maybe I should continue somewhere here. So if we denote by a and the number of n by n alternating sign matrices, then it's given by this very nice formula. So just a product of factorials. And that turned out to be a really difficult conjecture to prove this. And the first one to prove it was Seinberger. In a paper that was published in 1996, so 13 years later. And Seinberger's proof was really quite long and complicated. But very soon afterwards, Kuperberg, in a paper published the same year, found a short proof of this. And that proof uses the 6-vertex model. And actually with so-called domain wall, where you have the 6-vertex model on a square with the domain wall boundary. Conditions. So let me just elaborate a little bit about what Kuperberg did, because it's something I want to generalize in some sense. Okay, so this 6-vertex model on a square with these domain wall boundary conditions. That's a model where the states can actually be identified with alternating sign matrices. Well, even if it's not quite obvious that there's some bijection here between the states and alternating sign matrices. And if we look at the partition function of this model. So in the inhomogeneous case, this will be some function depending on many variables, x1 up to xn. That's y1 up to yn. And there's also a parameter that I did not q in the model. So that will be some. Roughly there's a sum over all these states times some weight function on the states. And I'm not telling you what this weight function is, but I will do it for a more general model a bit later. So the main point here is, well, the first main point is that there's a famous closed formula for this partition function, which is called the Isargin-Korepin determinant formula. It turns out that you can express this in terms of a determinant of, well, the way I will normalize this. A determinant of this form. And then, well, let's multiply by the denominator to make it a polynomial. And now it's anti-symmetric, so we can also divide by some Vandermonde determinants. Okay, so this. So this whole thing is a polynomial in all these variables, and it turns out to be exactly the partition function. So that's the first thing, and the second observation is that, well, really, Kuperberg's a great idea here is that if you specialize Q here to a cubic root of unity, and I will always denote a cubic root of unity by omega in the talk. It will appear again and again. And you also specialize all the x's to omega and all the y's to 1. And then you look closely at this weight function. It turns out that the partition function, in this special case, essentially just count the number of states. So zeta, the partition function will be some constant times just the number of states. So then what Kuperberg did was to use this formula. So apparently you want to make the same specialization of the parameters in this determinant. But then you see immediately that you run into trouble because, well, there's some singularity of very high order. So you have to make some limit and let the x's and y's tend to these values and try to figure out what the limit of the determinant is. And that's what Kuperberg found one way of doing and recovered these numbers in the limit. Well, and later other people have found other ways to take this limit of the determinants. That's quite a lot of literature on this. So the question for this talk will be, well, what about the more general model, which is this 8-vertex solid-on-solid model? So by the way, this name 8-vertex solid-on-solid model, it seems to be used mostly by Japanese, I think. So sometimes it's called the Andrews Baxter Forrester model, or well, at least in the case when this Q is a root of unity. But it's really a model that was introduced by Baxter in a famous paper in 1973, where he studies the 8-vertex model by in some way transforming it to another model, which is this 8-vertex solid-on-solid model. And that's a model that has, so in some sense it's very much like the 6-vertex model. So it has exactly the same states at the 6-vertex model. So in particular, if you have these domain wall boundary conditions, you can still identify states with alternating sign matrices. So what's different here is that we have two more parameters in this model. So there's one. Well, it's an elliptic model. It's described in terms of elliptic function. So roughly that's one parameter that makes it elliptic, and then there's one other parameter that will play, well, which plays quite a special role. So you can ask the question: what happens if you make exactly the same specialization of the parameters in that model? And it turns out that you get something quite interesting. So So for the six vertex model, we just got some numbers, which were essentially the number of states. So for the if you do the same thing for the eight-vertex solid-on-solid model, you will get something depending on these two parameters. And it turns out that it's something that also appears in the physics literature. You get essentially the partition function of the three-color model, which was also, it seems, introduced first by Baxter in a slightly earlier paper. Actually, I'm not sure if Baxter is or was ever aware of this limit. I mean, probably he would know it, but it seems that it has appeared in the literature only quite recently. But the main thing about this model is that it's really something completely combinatorial in nature. It's just defined by counting things, really. So you could hope that by doing this specialization for this more general model, you could also extract some interesting combinatorics. So that's what I spent some time trying to do. Well, and it turns out that the combinatorics should really be described in terms of these things that I call the three-colored chessboards. So let me say what that means. Okay, so this is something purely combinatorial, really easy to understand. So consider let's look at a chessboard of size n plus 1 times n plus 1. So n does not have to be 7 here. It could be anything. And then we paint. Let's paint the squares with three colors. And it will be quite convenient to think of these colors as being the residue classes 0, 1, and 2, mod 3. So these are the three colors we will use. And then we will have some rules. So the first rule is that neighbors should have distinct colors. So neighbors means neighbors vertically and horizontally. And the second rule is what domain wall boundary conditions amount to in this picture. So it means that if you look at just the boundary entries, the top left square and the bottom right square here will have color 0. And as you move away from this squares from the boundary, you increase all the time. And of course that should be red. Mod 3. So really what it means is that you cycle around these three colors when you go along the boundary here. So this is where I made an example. So is it visible enough, or should I turn down the lights? Well, so this is the example when n is 3, there should be 7 of these things. So for some reason instead of denoting the colors 0, 1, and 2, I painted them black, red, and yellow. So if you look at these examples, you see that the boundary is exactly the same on all these 7 boards. So you just have to fill in the 4 central entries in such a way that the neighbors have distinct colors. And if you try to do that, you see quickly that there's exactly 7 ways of doing that. Yeah, so we could keep this on maybe for a moment. So, well, sorry, let me just. Yeah, okay, let's do it like that. So. So I would just briefly like to explain here. So these things will be states of the model I'm looking at. So in particular, there should be some bijection between these and alternating sign matrices. So that's also something quite well known, but let me explain it because it will be maybe useful. So and the way I will explain this bijection is by defining a third class of things called height matrices, and then define bijections from that one to 2, 3 colored chessboards and to alternating sign matrices. And the height matrices, they will really be the description I will use in my description of the 8-vertex solid-on-solid model. So this is important to us. So height matrix, that really means something very similar, but you have instead of just having 3 colors, you color the squares with some integers. So you just attach some integer label to each square. And then the rules is that you have that neighbors differ by exactly 1 from each other. And you also have domain wall boundary conditions. And those will be exactly the same as over here. It's just that you don't read this model 3. You really plug in these integers here that you see on the boundary. And then the bijection from here to here, that's very simple. That's just reducing all the entries mod 3. So that's some observation that's been around since the 60s, that if you have a height matrix, it's uniquely determined by its reduction mod 3. So if you reduce everything mod 3, you don't lose any information. And this bijection here, that will be something that decreases the size of the matrix by 1. So if we have a matrix of size n plus 1, here we will have a matrix of size n here. And the rule is that you look at little 2 by 2 blocks of adjacent matrix entries. And then you imagine that you contract this whole block to a single entry. And the rule for doing that is simply that. So that that gives the bijection from height matrices to alternating sign matrices. We could do an example, just not because it's very relevant to the talk, but because it's amusing to do. So let's. So let's take a height matrix here, and maybe it's wise to take the one I prepared before. Okay, so this is a height matrix, because if you look carefully, any two matrices here differ by exactly 1. So the reduction to the chessboard, that's just given by reducing mod 3. So the 3's become zeros. So I guess you should be able to find that as one of these 7 examples. Whether that could be an exercise to find the right one. And if you want to go to alternating sign matrices, you should look at something like this plus that minus that minus that. That will give you 0. Similarly, here you will get 0, but here you get 3 plus 3 minus 2. That's 2, and you should divide by 2. So that will give you 1 here. And here I guess you will get 1, 0, 0, 0, 1, 0. So you see that this is indeed an alternating sign matrix. So it seems that this works somehow. Okay, so now, so that explains what 3-colored chessboards are and why they are in bijection with alternating sign matrices. And then I can say, well, very simple, what the 3-color model is. It's just to write down something like that. So you take t naught to the number of squares colored 0, and then t1 to the number of squares colored 1, and t2 to the number of squares colored 2. So it's nothing but the generating function for the, well, joint statistics of these 3 colors on the chessboard. But if you decide to call that a partition function, then it means you are considering the 3-color model. But I mean, it's really a generating function that counting. So that's what I mean when I say it's something purely combinatorial. Okay, so the main result I want to give is really some kind of, well, explicit or as explicit as possible formula for this thing. And let me write. The formula will involve theta functions. So what this 8-vertex-solid model tells us is that it's very natural to parameterize this t0, t1 up to t2 by elliptic functions, or maybe more precisely by Jacobi theta functions. So the notation for theta function I will use is this one, which is it's not quite classical notation, but nowadays it's a very common notation for theta functions. And also quite often I will think of P as fixed and just not write down P all the time. And I will probably use this kind of condensed notation. So if I write theta with many arguments, I will just something back. I just mean a product of theta function. So then the main result, which I don't quite have yet, because I haven't worked out the data, but I know what it will look like. It will look something like this. And now I think maybe you can switch off the light. I think Naomi, you have to do that. I will probably use mostly the camera from now on. Okay, so that's, well, is it okay? Can you see something on this? There's quite a lot of information on this slide. So first of all, I look at this three-color model with parameters T0, T1 up to T2. And then I choose to parameterize these parameters by two other parameters, lambda and P, by the rule that Ti is some, well, 1 over the cube of some Jacobi theta function. And note, by the way, that this thing is a homogeneous polynomial. So it's natural. Well, it's a homogeneous polynomial of 3 variables. So it's natural to parameterize it by 2 parameters, lambda and P. So you will not lose anything by substituting the Ti by this formula. Now, if you do that, it turns out that the lambda dependence on this generating function is extremely simple. There's just some huge factor here with lots of theta functions. And then you have a sum of 2 parts, and each of them is just a single single theta function in lambda. And you see also that this is kind of like the even part, and this is the odd part of this bracket I have here. Now the P dependence here. So I think, some of you have heard me speak about that before. So what's new here is that now I know something about these factors sitting in front as well. So they encode the P dependence. So Y here, that's a function only depending on P, not on lambda. And it's something explicit. It's some product of Dedekind eta functions that I didn't write down here. And the Pn's, they will be some polynomial, and they will have degree n choose 2. And I don't quite have a formula for these polynomials, but I have some kind of way to construct these polynomials recursively. And this Pn twiddle, that just means take Pn and reverse the order of the coefficients. Okay, and as before, omega is a primitive cubic root of unit. And as I will maybe comment a bit more in the end, it's possible that these polynomials Pn are really related to so-called Umemura polynomials, or at least some polynomials that have similar properties. But I'm not really there yet, so I can really claim that. So here's some examples of what these polynomials look like. So now it would be really useful if someone in the audience would just say that I recognize these polynomials and I can tell immediately what they are. So they could be related to some. Well, I think that they should be related to some some polynomials satisfy some kind of Toda type equation that I can't quite write down yet. But well, so this is I guess from the computer. So and also it seems that apart from some big power of 2 that has to do with the normalization, it seems that they all have positive integer coefficients. So I computed them up to 15 on the computer here, and they always have positive coefficients. I have no idea why that should be so. Okay, now I completely messed up all the papers. And here's I said that there was some recursive way of defining P sub n. So here it is. I don't know if you like it or not, but it will work. So I will look at a polynomial equation of this form: AP plus BQ equals C. So A, B, C will be known, and P and Q will be unknown. Everyone knows that you can solve such a thing by Euclidean algorithm, and the computer knows that too, which is quite useful. And here, so this will be a recipe for constructing Pn. So we suppose that Pn minus 1 and so on are all known. And the rule is, A is essentially Pn minus 1, but for some reason you have to plug in something extra here when n is odd. So B is essentially Pn minus 2, and C is essentially Pn minus 1, but then you have to reverse the order of all coefficients and square it. Okay, so then, of course, there are many solutions, but if you postulate that P has the same degree as B, I mean, usually you would postulate that P has lower degree of B, and then there will be a unique solution, a minimal solution. But if you say that P has the same degree as B, then you expect a one-parameter family of solution. And you pick a point on this line by postulating that Q at minus 1 should be 1. Then it turns out that the solution here, the Q part of the solution, that you can define to be your Pn. So I don't know if this rings any bells with you. I haven't quite seen a family of polynomials defined like that before, but yeah. So the object of the rest of the talk is to try to explain very roughly where this comes from. So maybe I can write down. So this looked quite strange. Maybe I can write down the trigonometric case for you because it's more easy to understand. So if you take P equal to 0 in all these formulas, then the theta function will just be 1 minus x. So what this says is that you take this 3-color generating function and plug in these special values of the parameters. Then you again have a huge factor comes out in front, and what remains is a small factor. And you see, by the way, that when lambda is 0, then this just reduces to the number of states, and this reduces to an. So an is this alternating sign matrix numbers. So Cn is another number, and it's quite amusing that this is also a number that's kind of famous in combinatorics. It counts cyclically symmetric plane partitions. If you know what that is, it means plane partition with a certain symmetry. So this is quite a nice formula. You can immediately apply it to get some non-trivial information about these 3-colored chessboards. So one thing, so I said that if you put lambda equal to 0, you get just the alternating sign matrix theorem. So it's quite natural to look at the next coefficient of lambda. So you look at the derivative at lambda equal to 0, these things. And then it turns out that if you do that, you have computed the probability that if you take just a chessboard completely at random, and then take a square from that chessboard completely at random. And here there are absolutely no weights involved. It's just uniform probability. Then you can ask for the probability that this square has a certain color I, well, where I is 0, 1, and 2. And that's something that falls out if you do that. Which is quite nice. And here I just give a sample answer. So the answer depends a bit on what n is to mod 3 and what I is. So for instance, if you suppose that n is divisible by 3 and you look at the squares with colors 0, so those were the black squares in the picture I had, then the probability will be, so I mean, 1/3 is what you expect, of course, when n is big. So if you take a big chessboard, roughly 1/3 of the squares should be black. And then the amusing thing is that you have an exact formula here with two very simple correction terms.
If n is even, doesn't add up to 1, big probability. Or they're different, of course, for other i's. Sorry.
Yeah. Yes.
I
Yes.
take it back.
So yeah. So I didn't write down the complete answer, but for other I and other n, you have essentially the same thing, but maybe this 4 will be a 2 and this 2 will be a -1 and so on. Yeah, exactly, to make it add up to 1 in the end. Okay, so this I think is quite well, it's quite neat results, and since it's quite kind of one level deeper than the alternating side matrix theorem, I don't believe it's something that's very easy to prove by some kind of direct method. So this 8-vertex-solid-on-solid model really seems useful here. Okay, so I'm really yeah, thank you. So I realize I really planned the talk a bit badly, so there's no way I will be able to say everything I would like to say. Okay, so let's just say something quickly about the 8-vertex-solid-on solid model. So this so I'm supposed to finish in 5 minutes, or should I? Do I have? Yeah. Okay, maybe I can just flash for you the Boltzmann way to this model and try to explain how this thing works. So the states of this model will be the height matrix. Will look something like this. And the kind of Boltzmann weights, the weight of this model will be described by Boltzmann weights. And the Boltzmann weights are attached to these blocks of adjacent matrix entries. So if you have a block like this, which is at kind of, it is kind of in the ith row and jth column here, and has entries A, B, C, D. then this block will have a weight weight given by this rule. And if you're familiar with the 6-vertex model, but not with this, the main thing here is really this extra variable lambda, where you have to shift lambda actually by q to the a, where a is the actual entry of the Heine matrix at the, well, the upper left corner here. And the Boltzmann weights, they are given by theta functions, but by these formulas that are maybe not so interesting to look at. So if you sum the weight, okay, so maybe I should write. So for any state, you define the weight to be the product of the weight of all these blocks given by this rule, and then you sum over all states. Then you get the partition function of the model. And that will depend on x variables, y variables, and a variable lambda. And it will also depend on two extra parameters here, p and q of the model. And it turns out that if you make this specialization when q is omega and all the x's are omega and all the y's are 1, and look really carefully on these things and think about it. You will see that this 8-vertex SOS partition function will be equal to some elementary factor times the 3-color partition function. So this one just depends on T0, T1, and T2, where Ti are given by the formula I said before. So I realized this is not very clear, but anyway, you can see that happens. So the appropriate generalization of the Isao incorrect indeterminate identity, I claim, looks like this, which looks really, really complicated. But I believe that this is in some sense, the best thing you can get in general. So in the results I showed you about the 3-color partition function, they actually follow from this formula, but really not using the formula, just using one very interesting property here that I want to point out, that so if you look at this as a function of lambda, okay, I will finish in a minute. So you see that, well, the point is that if you just write down this thing, it will look like it has lots and lots of singularities in lambda. But if you look at this formula, it only has single poles in lambda. There's also some pole depending on gamma. But gamma is just an arbitrary parameter that doesn't enter in on the left-hand side. So these poles have to be removed. There's only some single poles here. So in particular, if Q is omega, then this that can really only be poles at 2 places. So this factor could have poles at 3 places, but one of them is killed by that one. So if you write down something like that, that would be really an entire function, or, well, it's singular at lambda equal to 0, but holomorphic for lambda non-zero. And if you recall the formula I had for these 3 color partition functions, that was some very simple dependence on lambda, and that really comes from this factor. So what I also wanted to explain was why the p dependence in lambda comes from these polynomials Pn defined by some strange-looking recursive procedure, but I will not have time for that. So I finish here, and maybe if you're interested, I can talk to you in private about this other things. Okay, thank you. Yes.
Again, the regression on the polynomial. What it seems to be first order with nonlinear first order with all 7. The n minus 1, the n minus 2.
So you wanted to see the
recurrence.
The recurrence. Yes. So provided I can find. Yeah, here it is.
So A is Pn minus 1, B is Pn minus 2, and the C is some reshuffling of Pn minus 1. So it depends only on 2 indices. Pn minus 1 and Pn minus 2.
Yes, it's like a 3-term recursion.
Q is Pn.
Yeah.
Oh, okay.
Mm. So what this really comes from is to look at something like so what we want to do is to look at, take all the x's equal to 1, omega and all the y's equal to 1. So what I do really is to take all the x's equal to omega except the first one. And this will give some function of t. And that one I can prove satisfies some genuine 3-term recurrence relation, which is quite explicit. And it follows from that one that this Pn, which is roughly like Fn at the point 1, will satisfy some equation like I have here. Yeah.
You had a list of some of the polynomials,
Yes.
and I noticed that all the ones you displayed had degree that was a multiple of 3 except for 1. I just wondered if that was a misprint, or are they all supposed to be
No, the degree should be n choose 2.
there?
Mm.
Angular.
Yeah. So yeah,
Indices.
the degree of Pn is n choose 2. So I think it looks right to me.
Sorry, I can't see what you wrote.
Oh, I'm so sorry.
Okay,
Yeah.
thank you.
So it's just a coincidence, I guess, that many of the first one are divisible by 3.
Yeah, I have a couple of questions.
Yes.
The determinant on your last slide, if
Yes.
you take S equal to the full index set or the empty set, isn't it just a Cauchy determinant, a Frobenius determinant?
It's always that. So you can always, the determinant I had inside the big sum, you can always write.
Evaluate it in
Yes,
terms of
it's always
Frobenius
factors.
identity. Is that what you're saying?
Complete. Yes, yes.
Okay.
Yes.
Yeah. Okay. Well, because you have such an explicit formula, I wonder whether you can take the infinite volume limit. That's really my next question. I mean, in the case of the 6-vertex model with domain wall boundary conditions, you can.
Yeah.
And the result is different from when you take periodic boundary conditions, which
Yeah.
can be understood from the fact that you sit at the critical temperature of the 8-vertex model. So then you cannot expect independence of boundary conditions. Whereas in this case, you're away from the critical manifold, so you actually know what limit to expect, namely Baxter's free energy. Baxter has figured out the continuum limit, the infinite volume limit, sorry, of the partition function with periodic boundary conditions, right?
Yes.
And here you expect independence of boundary conditions because you sit away from the critical temperature. So you know what limit to expect for that formula. When you divide by, you take the log, divide by 1 on n, and take n to infinity.
I mean, you probably know much more than I do about this, but I mean, the 6-vertex model is some special case. So if you have dependence on boundary conditions there,
it's at the critical manifold of the 8-vertex model.
Ah, I see.
This is in Baxter's book. It's all in Baxter's
Okay.
book. You can reformulate the 8-vertex model in terms of an Ising model, where there is 2 interlaced Ising models with couplings between the 2, and it's for very special couplings that you get a 6-vertex model, and it's precisely where this Ising model is at the critical temperature. So because there you're at the critical temperature, there may be dependence on boundary conditions, and yes, there is, because you can in both cases evaluate the limit, both for domain wall and for periodic, and they're different. Right? But you do not expect this difference to persist as soon as you are away from that critical manifold. So that means that you can sort of know beforehand what limit of your formula should be, which of course is much easier to aim for.
Yeah, so I didn't try to do it directly from that determinant formula.
That's the name of the game in statistical mechanics, right? That you want to take the infinite volume limit and find the free energy. Here you seem to be more interested in having the result for finite volume, for just a square lattice that's finite.
Yes.
But
so
as
for
a physicist, you really want the infinite volume limit for energy.
So what I was hoping to try was, so if you take instead all this x is equal to omega t, then for the 6-vertex model, what you have there, that will be a solution to some total chain type equation. And that's used, as you well know, to study the infinite volume limit of that.
Yes.
So I was
it's much
hoping
simpler
to-
for domain wall boundary conditions in the 6-vertex case because you can use Toda, the Toda lattice.
But I think there's something like total lattice also here. In this.
So you're saying there's also here a Toda lattice lurking in the background?
I think so, but I haven't really came to the point where I can write it down explicitly. But for some reasons, I think there is.
So, are there any questions, comments? No. Oh, let's thank the speaker once again.
Yeah. Okay.